Thanks. So thanks for the intro, and thanks for coming to the talk. Thanks for the invite to speak here. As you said, I graduated from this university, so it's kind of nice to come back for a visit after a while. So as Michał said, I'm from the AI for Science team at Microsoft Research, so maybe I will have a bit of a slide at the end as well, but maybe to give you a bit of a background so you know where this is all coming from. So this is maybe a fairly new initiative. I mean, the first things that we've done on drug design, that was maybe 3 years ago, and then we really started scaling up the team maybe a year ago. And it's really a team that is looking into applying deep learning into various problems in the physical sciences, so physics and chemistry. And this in particular includes drug design, which is the sort of sub-part that I'm in. And you could ask, well, how come Microsoft is trying to design drugs? I mean, you know pharma, right? And that's fair. We are lucky enough to be collaborating with pharma, though. So we have a collaborator, which is called Novartis, aka Big Pharma. So we're lucky to have a collaborator that kind of helps us with these things, and also they act as a sort of a early beta tester, if you will, of the stuff that we do. So a lot of the things that we do is not kind of random research papers. It's actually things that people at Novartis take, and they actually use it, and they kind of test it in practice. Right, so in this talk, I will tell you about reaction prediction and retrosynthesis. I will sort of outline the problem. I will tell you about some solutions, ideas, models. Many of them come from our team, or sort of early works from our AI for Science team. Other things are sort of just interesting ideas that people had and that were cool enough that I figured I can include them here. And then in terms of sort of meta things, so feel free to ask questions at any point. If it's like clarifying questions, feel free to just interrupt me. And then there will also be, I think, 3 points during the talk where I will stop for questions explicitly, kind of checkpoints, if you will. So let's start with small molecules. These are the objects that we'll be manipulating in this talk. So instead of giving you sort of a very formal definition, I can just show you a bunch of examples. So molecules that look kind of like this. And kind of keeping in spirit with all of the deep learning lectures nowadays, instead of showing people real things, you show them samples from a generative model instead, and you see if they figure it out. So of course, these are also samples from a generative model. But they are sort of representative kinds of what you see in drug-like molecules. There's a reference at the bottom. We'll get back to that model in a second. But these are the kinds of molecules that you're interested in, and they're pretty important. If you want a more sort of headline thing, you would say that they change the way we live and die, right? These kinds of molecules appear all over the place, from sort of organic materials and sort of agriculture, all the way to drugs, right? So all the way to medicine that literally changes whether you live or die. So when you are a pharma company, a big part of your sort of business is to figure out, how do I design these small molecules to fulfill some certain properties, and then how do I synthesize them in the lab and hopefully make them into some useful medicine. So let's go over how drug design works in say, a pharma company like Novartis. So it's usually this sort of iterative process when you have designing, making, and testing a compound. So designing is really coming up with an idea. You can think of it as a drawing on a piece of paper. So you design something that you think is going to have some properties. Then you would make it in the lab. So you go from an idea to actually having physically that compound in a vial or something. And then at the end, you would test it. So you would go and maybe check if it has the properties that you wanted. So if it's like soluble or non-toxic or binds to a particular protein. And then this test step gives you some measure of goodness. And then you go back around and you try to optimize this measure of goodness through this loop. And then there are many interesting questions in this process, right? One is the generative question. So you can look at the design step. And I think actually most of the machine learning papers in drug design most of the machine learning papers tackling this whole thing focus on drug design. I mean, it's kind of a cool, sexy problem because it's a generative problem. So you can train generative models and make novel things and so on. And so this is something that we started with. So we started by looking at this design step. And I should, of course, say that normally this design step is done by chemists who have some intuition of what's going to work. But you can also apply machine learning models here. So you can train generative models. And this is actually a part that I will not tell you much about. So this is our earlier work. But feel free to ask about this. So I'm just giving you some pointers, but feel free to ask about the design part as well if you have more specific questions. But this is what we did initially. So we did some generative models of molecules. This is the model that produced the molecules on the first slide, by the way. And there's a pointer to a paper published on iClear, which is cool, I guess, but maybe not super unique. So many papers published on iClear nowadays. Maybe a more unique feature is that this model is actually used by Novartis, right? So the samples that come out of these models, the chemists have seen them, and they kind of like them, and they made them, and they made sense. And then maybe the other feature is that the code for this is open source, and the weights are also open source, so you can just pull the code and ask for some samples and see how they look like, so you can play around with this. But then this talk will actually focus on the other step, on the make step. And if you think about this, the make step is a bottleneck in this whole process. And in a way, you can be as creative as you wish in the design step. You can come up with super creative molecules, and maybe even theoretically they have the properties you want. But if you can't make them, they are essentially useless, right? So you're bottlenecked by your ability to actually make things in real life. And then this is a bottleneck even if the designing is just done by chemists, but it's even more of a bottleneck if it's done by machines. Because on average, chemists will have more of a better sort of prior and more of a better intuition and maybe bias towards things that can be easily made, whereas machine learning models, especially unconstrained ones, will more often generate things that are just hard to make. So this becomes even more of a bottleneck if you introduce machine learning to the design part. So in this talk, we'll talk about how we can tackle this make step, right? So how we can figure out how we can make a molecule that we've sort of decided upon in the design step. And then here you can maybe stop and think, like, how would I make stuff, right? Where would I take molecules from that I have designed on a piece of paper, right? So some of the molecules if you're sort of lucky, then your molecule is something called a natural product. So it just occurs in nature. So things like, caffeine, a very useful molecule, you probably had your fair share of it during this conference. So things like this happen to be produced by some natural process, but most things isn't. Most things aren't. So most things that you can think of, they just don't happen to occur in nature. So you need a more systematic way to make them. And I'm sort of foreshadowing here. We'll go into the details, but essentially, chemical reactions are this hammer that you're going to use. And if you're good enough at using this hammer, you can, starting from simple things that you can obtain otherwise, you can build more complex things and sort of arbitrary-ish things. So we have to talk about chemical reactions now. So you probably have, is there a question or?
Yes. So my question is related to yesterday's talk, just 24 hours ago, the guy who was at AstraZeneca. And so the methods he presented are on scoring, like ranking molecules. So what's the relation of like choosing the more, like the easier one to synthesize versus scoring which one is the better to have in the end? So is this related or like?
Mm-hmm. So was his stuff, for example, about predicting properties and scoring, binding, and yeah. So that would be, so as I said, the properties, if you're measuring properties, you would be measuring them in the lab, so in the test parts. But of course, that's a very sparse signal, right? So if you're doing the design step sort of in a more principled way, then what you would do is you maybe would have some machine learning models like the ones presented yesterday, and then you would use them, you would have a smaller loop running inside of this design step. When you have machine learning models, because as I said, I pointed you to a generative model. This is an unconstrained generative model. It's sort of like a VAE on graphs. And then how you actually use this in practice is you would have this model and you would run some sort of inner optimization and you would optimize against some learned model, like the ones presented earlier. You could have also learned proxies for synthesizability, so sort of models that try to approximate whether the molecule is going to be easy to make. And then you sort of have many learned functions and you optimize against that. And then that is what falls out of the design step.
Okay, thank you.
So these learned models plug into the design step here. And you can also try to invert things a little bit and try to make the design step sort of be biased towards things that are going to be easy to make. but it's only just a bias, right? In the make step, we're going to actually figure out how to make things, and not only just push ourselves in the region that is maybe more synthesizable. So you probably already have some cartoon view of chemical reactions, right? We have some things that we mix together under some conditions, magic happens, and other things come out, right? And probably that view is more or less sufficient for this talk. So chemical reactions are this thing where you have some molecules, we call them reactants, and then we have some conditions, some also catalysts, reagents, so kind of other things that are around that facilitate the reaction, and then you have products that come out. And then some mental view of this is that the reactants, it's a bunch of atoms connected in some way, and then due to some chemical reasons, these atoms rearrange somehow, and some of the bonds are broken, other bonds are formed. So if you think about this, the left-hand side and the right-hand side is actually the same set of atoms, and most bonds stayed where they were, if you align things properly, and some of the bonds got broken and formed. And we'll formalize this a bit more in a second. So that's kind of how reactions look like. And there's this one other thing. So it will be useful later in the talk. If you're asking how you're representing these things, we usually think about molecular graphs. There are very nice representations for these kinds of things. But in some cases, you might want to convert these things into a sequence. And I think some of the talks already mentioned the Smiles notation, which is a way to linearize a graph. And then if you do this for all of the molecules in your reaction and you concatenate that, you have a string that describes a reaction. So this string basically describes the reaction at the top. I won't talk much about Smiles notation. I mean, I think it's pretty obvious. You can linearize a graph. You start somewhere. You kind of walk around, and you list everything you see. And it's not a unique representation, because otherwise you'd be solving the graph isomorphism problem. But it is a representation, sometimes useful. So that's a reaction, right? So what problems could you think of? Before we go back to the make step and see how all this is useful, one simple problem that you could think of, some machine learning problem, would be essentially simulating physics, right? So saying, these are my reactants and conditions, everything, what would come out, right? So that would be left part being input, right part being output. But maybe if we start thinking back to our make step where we had something that we wanted to end up with, then it's kind of the other way around, right? We want to end up with something, so we kind of know the product side, and we want to figure out the reactant side. So maybe we want to do something called the backwards reaction prediction problem. And then before we go even deeper and see how this is useful more practically, because you could think, well, this backwards reaction prediction problem isn't really solving my thing, because I have some product, and then maybe I apply this, and I get, if you had these reactants and you reacted them, you would get this product that you wanted. But I don't have the reactants, right? Maybe they aren't even easier to get. So maybe I reduced my problem from one molecule I don't have to two molecules I don't have. So there's probably some more of a planning and strategizing element missing, and that will come in a few slides. But just to first maybe compare these forward and backward directions. Because you could say, sort of thinking a bit naively, that it's like a translation problem. It's like Polish to German, German to Polish, kind of the same thing. But it happens that the backward direction is actually the harder one. So just to show you quickly some reasons why. So one reason is that when you look at, for example, some databases of reactions, they are usually extracted from papers and patents. And then when chemists report reactions, they care about some interesting product that was formed. And often it's the case that some product was formed, and then there was this other stuff that also got formed. But that was uninteresting. We just got rid of that. So for example, this reaction is actually the same reaction as here, just plotted with different software. So you can see on the right-hand side, there's like a bigger product and maybe like a small product. And if somebody didn't care about this small product, they would say it's a side product, and they would maybe not report it in your data set. So then, if you think about this, if you look at this data set, I said that the set of atoms on the left-hand side and right-hand side is the same set of atoms. But that's only true if you report everything, and usually you don't. So then you end up with usually this case that the right-hand side is like a subset of the left-hand side. So if you're doing left to right, if you're doing forward, you have to sort of delete some atoms. If you're doing right to left, you have to invent back some atoms. You have to think back, I wanted to end with this product, but maybe there could have been some side products. What could have been those side products? And then go back in time and go to the reactant. So you can see the backwards is sort of more inventive. And one related thing, but it's not quite the same thing. It's also quite natural. You can get the same product in multiple ways, right? I said forward is like simulating physics. So predicting what's going to happen if I mix some things together. And forward prediction is, you could say essentially there's one answer. I mean, there could be like quantum effects and different things could happen, but maybe there's like one dominant thing that could happen. So forward is kind of like a single answer. Backward is really not a single answer. Part of this is because of this side product omission. So you could say that this product here could be made into two different reactions, and these two different reactions actually had a different side product that was omitted. But there could also be other ways where it's not only the side product omission that leads to this. So in general, there can be many there's a single answer to your question, but there can be many questions that give you this answer, right? So going backwards has multiple correct answers. So it becomes a bit tricky to evaluate, right? So generally, backwards is harder, and it's harder to evaluate as well, because if you're going forward, there's like a ground truth in the data set that you compare against. If you're going backwards, maybe your model is producing something that doesn't match the data set, but it's correct anyway. So it's kind of hard to reason about, but at the very least, when you have a backward model, you would ask it for several answers, and then you would say, maybe in my top 10 answers, I check how often I recover the one from the data set, and if I don't, then maybe the model is more wrong than right, because it's weird that there are 10 answers and none of them are the one that was from the data. But of course, this is not very exact.
So, isn't it the case that for the forward, we have always some kind of like a slow verifier? So, if you want to do evaluation of your backwards problem, you could go through this slow evaluator and then check if this really...
You're talking about some, for example, physical simulation and things like this. I mean, of course, we have a verifier of actually running the reaction, but that's pretty hard. You could run some chemical simulations, but that is, I mean, I'm not directly working with these things, but as far as I'm told, these things are generally tricky. So in some restricted sets of reactions, if the molecules aren't big enough, you can take the reactants and kind of simulate things forward. But if the reaction is complex enough or big enough, then these things don't typically work. But yes, this is a good idea in general, that the forward can verify the backwards. It will actually appear later in the slides. And we are also thinking about, can we use actual more principled physical simulations? But at the moment, it's a thing that you can use in some cases, but it's not a very general thing. And even if you can use it, it's more expensive to perform. And then kind of ending, this will be the last slide of this intro to the problem. So we'll go to retrosynthesis. I mentioned that going backwards one step is kind of not very principled, I mean, not kind of directionless. You need some sort of planning to go with this. So we have this retrosynthesis problem. So we can define this in various ways, but one way is to say that we already have a backwards reaction model, right? A model that, given a product, gives us possible reactants that would give us this product. And then we also have a target molecule, so the stuff that falls out of the design step, and we have a set of building block molecules. So these are molecules that you assume you don't have to make full reactions because you can just go to a random molecule shop and just buy them, which sounds kind of weird, but there are actually companies which have a big menu of simple molecules, and they say, you can order this molecule for this many dollars. And so what you eventually want to do is you want to start with your target molecule and through a sequence of reactions, decompose it back, or if you invert time, start from the building blocks and through a sequence of reactions, arrive at the target, and the building blocks you just buy, and then you run the reactions. That's how we get arbitrary things. So this is an example of how this answer could look like. So the question is the target molecule, and then the answer could be this picture. So it shows, target molecule comes from a reaction of these two things, and then the first thing comes from a reaction with a single reagent that can happen, because maybe some conditions make it react, and then this one comes from these two, and maybe these three are purchasable, so you can buy them and run the reactions like this. And maybe one important source of confusion here, and we'll get back to that later when we start talking about doing search. If you're familiar with doing search in games, like in Go, on chess, you might be it might look familiar, like it's like a search tree that has some children and stuff like this, but it is really not, right? In chess, let's say, you would have a search tree that searches various possibilities. It branches out, but then a particular chess game is a path down this tree, right? Whereas this, a path down this tree is not particularly meaningful, right? This whole tree is the game, right? It's not a single path here, because this branching doesn't mean we choose either of these two things. We have to get both of them to get our target. And it will become more confusing later when we start thinking about search, where the branches sometimes actually mean things that are either or, and sometimes they mean things that are both. So that's just a source of confusion to watch out for. And as Michał said, you could ask, how does the forward model fit into this? So you actually asked about sort of forward models implemented by simulation, but you can have a forward model implemented by machine learning. And these are still useful because, as I said, it's an easier problem. So what people often do is they have a forward model to kind of double check the steps. So you make some backward step, but then you have your forward model, which is maybe stronger because it's an easier problem. If the things don't agree, then maybe it's kind of a shady step, and maybe you don't want to do this. So that's how the forward is useful. So that was the sort of intro part, and now I have sort of basically what's coming. There's one section of slides with a deeper dive into kind of ideas and models in single-step prediction, so predicting the reactions for a single step. It's kind of like a translation task. There will be another section with a deep dive into search. And then there's one more section with sort of our more detailed experiences with trying out the state-of-the-art things and seeing some of the weird discrepancies. We might not have time for that last section, depending on other things. But this is maybe a good point to stop for questions, if there are any questions for the sort of general problem setup before we go to any details. Otherwise, we could, yeah. This.
So just one question, not all the reaction that we want is visible. So how do you do that? Maybe you find some molecules that your graph says that this reaction can happen, but the reality is that normally there are lots of other things than a graph that play a role.
So so you're asking if we can, or is that a statement, or is that a question? Sorry.
I want to know that how do you put that thing that some molecules don't react to each other? Oh,
some things just won't react, right? Yeah, so that's generally a tricky thing, because if you're training a model from data, then usually you don't have negative data of things that don't react. So if you're training a backwards model, then it's maybe less of a problem. You have a backwards model that proposes some reactions, and some of them may be just wrong. Some of them might just not react, right? So that's the thing you have to deal with, and eventually, you would find some retrosynthetic routes, and they might contain steps that just don't work, and so in the end, you have to check them somehow, right? So the only kind of ground truth way to check them is to run the reactions in the lab. In the forward direction, the negative data, the lack of negative data is a bit more problematic, because I said that you could use a forward model to double check the steps. So then if you had a forward model that had an option to say these things don't react, then it would be a nice thing to do the double checking, because it could actually say these things don't react. And some models do that, but then if somebody is designing a forward model, often they just have a forward model that says, given this reactants, what's the product? And it's again a bit of a problematic setting if you put two reactants that don't react, because what the model will do, it will just produce something. It will guess the product kind of under the assumption that they react, because these were the only things that it saw in the data.
So you don't use any thermodynamic rule for that. You just have graphs.
Yeah, it's all kind of deep learning flavored. So it's predicting, say, graph transformations and things like this. As I said, we have actually in my team this whole other part devoted to more kind of principled physics things, and then you can think of simulations and things like this. So it has a role, but it doesn't answer all the questions, basically. We have to figure out how to combine them, right? So in which cases we maybe use the more expensive, more principled thing, in which cases we use the deep learning thing. That's still kind of an open question, but this thing have a role, but they don't appear much in these slides. This is more of the deep learning kind of part.
Could you maybe comment more on how the backward reaction model works? It is a little bit confusing to me that it was an input to the retrosynthesis problem.
Yeah, you could define it in various ways, right? What I meant to say is that this backwards reaction model, you train it sort of separately, right? So you say your task is to predict this reactions backwards, and then you train it, and then you have that model, and then you go and you do the search. So that's why it's kind of shown as an input. So the idea is that once you have this backwards reaction model, it's kind of like an environment that you play against, right? If you think of the game analogy, the backwards reaction model tells you what's allowed, so it tells you what are the allowed moves in the game of retrosynthesis. But it's maybe a weird thing to say it's an input, right? You could also define the problem as the whole thing, where I guess your input is instead a database of reactions, and the first step is turning that into a reaction model and then using that in search, yeah.
Maybe a follow-up question. So this backward reaction model takes as an input the output molecule, and does it take anything else as an input? Because I imagine it to be a deterministic model, and then what makes it possible that you can get different outputs? Let's say.
Oh, how do we deal with the fact that it can produce many outcomes? You mean? Yeah. So it would only take the product that you want. So it wouldn't be normally conditioned on other things. I mean, some people do like conditioning on what type of reaction I want to have, but this is not really used in practice. So I wouldn't do that. So it just takes the product, and then it has to have some probabilistic thing inside. So one thing is that maybe it has some classification layer somewhere. We'll see in a second what can we classify, but maybe it has some layer with probabilities, and then you sample from it. Maybe it has some autoaggressive process, and then again you sample from it, or you do beam search in that autoaggressive process. So it is a deep learning model. It has some probabilities inside, so you have to figure out where to sample or where to sort of beam search.
All right, thanks.
I guess we can go to the deep dive. So I have this slide, which might be a bit confusing because we will have a lot of references, I guess, more for if somebody later wants to read all the papers in the world, then they can look at this. I just wanted to make a quick point about if you look at these reaction models, basically like a taxonomy of how they can look like. And this is maybe not a taxonomy that you see in the literature, but this is how I like to think about this. So one way to divide these models is basically and we're talking about deep learning-based models here, so we're kind of limiting ourselves to that. So it's either more end-to-end or more edit-based, which basically means that end-to-end means that we have some model that has like an encoder and a decoder, right? It decodes the products and decodes the reactants, right? And it's end-to-end in the sense that it's kind of, it doesn't make any special assumptions about the problem. It just consumes one graph, outputs another graph. So it's kind of like a translation problem in the space of graphs. So that's the kind of the first flavor, and the other flavor is edit-based, which exploits the fact that in reactions usually only few bonds change, right? So instead of kind of funneling your input and then kind of expanding it back out, you can try to predict the edit, kind of try to predict the difference between one graph and the other graph. And of course, it's not very clear yet how you do that, but these are the models that have this bias towards not changing things, and they try to only predict the little bits that change. And then to just give you a bunch of sort of deeper taxonomy references, end-to-end, you can really use anything that can like consume a graph and then output a graph. So we could use GNNs. The reason that people more commonly use transformers on the Smiles notation in this case is, I guess they're maybe slightly easier to set up, because when you have a decoder of graphs, it's kind of like an autoaggressive process that has many different answers at each step, and it's maybe a bit more annoying to think about. So most people in this end-to-end area, which is, by the way, we won't talk about this much, this one much here, I think is kind of less interesting, but mostly people would use something simple like a transformer that consumes one smile string and outputs another smile string. And then the edit-based part is more interesting, and it's more kind of problem-dependent. So here comes an idea of templates, and this will be explained later. But basically, when you're predicting this edit, you either predict it in sort of one shot, when you predict everything that changes, and that's called a template, and you sort of apply this rule to your product, and after application, you get the reactants. And there are various ways to set it up. Some of them we won't touch upon, but just to mention that these edits can also be produced in sort of more steps. So you can think of there are also models that take many little steps and kind of predict kind of element by element everything that changes. And it has some caveats similar to graph decoders, I guess. But this can be also done like this. So you have, keeping it abstract for now, you're predicting the edit somehow, you're predicting the graph rewrite somehow. And then there are a bunch of papers in each of these, so a bunch of references if you're interested. Some of them will be featured later in these slides, but many won't. So on the end-to-end side, as I said, is kind of the less interesting one maybe. So end-to-end is just kind of like a translation problem. You encode one smiles or one graph, and you decode another one. And these models are quite popular. I mean, they are easy to set up. They work well in some cases. They have a bunch of drawbacks. I won't maybe list all of them. In general, one of the drawbacks is that they have to copy a lot of things because a lot of stuff doesn't change from left to right. So they have all of these kind of copy problems. There are some special transformers for this. They also sometimes hallucinate, so they would like make up an atom, like a gold atom appears out of the blue, because they're pretty much unconstrained. It's kind of standard deep learning territory here. And they have, in kind of more, sort of more intuitively, they have various problems around covering the entire distribution of possible outcomes. So they are often reasonably good at giving you one guess. But as I said, in backwards models, you typically want to have more possible answers. And then these models are empirically worse at this. One reason is that if they use this smiles notation, right? This, as I said, this is not unique, right? There can be many strings that give you the same graph. So annoyingly, you can sample from a model like this and say, I want 10 samples, and it gives you 10 technically different strings that map to the same graph, right? One reason why this happens is that because this is non-unique, people usually would construct for a single graph many different stringifizations and train it as like a data set augmentation thing. But then the consequence is that at inference time, you get all of these variants of the same thing. It touches upon these sort of symmetries or some sort of ambiguities in this. So in general, they are not as good as if you look at 10 outcomes. If you want sort of a better coverage of possible things, they don't work as well here. And what works better and what's maybe more interesting are the edit-based approaches that try to predict the diff. And that's kind of based on this intuition that maybe if you have these molecular graphs, maybe not many bonds change. So if you squint at it, if you take these bonds that are sort of circled here, if you break them and then you kind of reassemble the pieces, you can get from left to right, right? So you could say that the rings kind of stayed intact, they didn't break. And then, so these edit-based models try to predict the difference, but then if you think what difference means, it really hinges on this assumption that we have some sort of a correspondence between left and right, right? The last slide didn't have a correspondence, so you intuitively know that this bromine went here and this went there, but it's not obvious that this is what happened. And in fact, if you run some reaction in the lab, as far as I know, it's not really easy to kind of figure out where the atoms went, right? You have some molecules at the end, and then you can try to infer maybe which pieces went where. So in fact, in order to start talking about the diff, you have to have some way of mapping reactions. That's called the atom mapping problem. You're trying to map left-hand side to right-hand side. And then if you're more sort of computer science minded, this might start sounding like things that you could tackle, right? Maybe you want to see something like a maximum common subgraph left to right, or maybe it's kind of like an integer programming kind of problem when you're trying to minimize some bond deviations between left and right and optimize overall permutations. And you can do things like this, and there are many tools that do this, and they work reasonably well. Here I want to highlight one tool which is more recent, and it also works well, and it's based on deep learning. And I think it's a very sort of cool idea, and it's maybe an unexpected idea that something like this even works. So how would you apply deep learning to this? You could say, oh, I just take some data and train a model. But the thing is, where do you take the data from? Where do you take your ground truth atom mappings from? If you take them from a heuristic based on maximum common subgraph or things like this, then you're just distilling a heuristic into a model. That's not maybe super interesting. So if you don't have, at least you don't have large amounts of data for this, then how would you apply deep learning? There's this one interesting work. We didn't have anything to do with this, but it's very neat. So it's actually almost fully unsupervised, and it's based on this idea that you can linearize these reactions into these reaction smiles, just for convenience of being able to apply transformers. And then you train an unsupervised transformer to do masked language modeling on this, so kind of BERT-style kind of model, which is kind of related to the task of reaction prediction, right? Except you're not masking the entire reactance, you're masking random bits. And then intuitively, a model that is good at this probably understands atom mappings to some extent, because you're training it on unmapped reactions without these little numbers. And then intuitively, if you have such a reaction, you masked some stuff, you masked an atom in the product, a nice way to recover that atom is to figure out where it was in the reactants. It probably didn't get mapped there, so we can just copy everything over. And so if you have a model that is sort of good at masked modeling reactions, then you could say maybe it understood atom mapping somehow, but then how would you extract it? And the weird thing is that you look at the attention pattern, so it's a transformer, right? So you look at layer 11 at hand 6, and you look at the pattern, attention pattern from the product atoms to reactant atoms, and you kind of just see the atom mapping, right? And of course, you could say, wait a second, like, why do I look at this particular head? Is there a question, or?
So what is the unit of masking here? This is a single atom, or you mask the whole molecule?
Yeah, I actually don't exactly remember from the paper, but I think it's a token, so it's certainly not a molecule. So it's
more than a molecule, so it can be
smaller. Yeah.
But it can be a couple of atoms, for example. It's
okay.
Something with geometrical structure, like for example, 3 atoms in some strange connection.
So I guess you'd have to double check the paper, but I think it's just splitting the smiles into individual symbols, and then you probably just do this randomly. So it would be like on the atom level. There's certainly its own smiles, so it's kind of limited geometry that's in there. If you use some sort of a tokenizer, like there are this tokenizer that merge common core-carrying pairs of tokens, then you kind of end up with like little chunks of smiles as being a single token. But I think for this particular case, you don't want to do that, because you want to think about attending from one atom to another atom. And you can see there are like all these little smile symbols down here, and they attend to different things. Even the parentheses that aren't an atom, they attend somewhere. So I think it's kind of on the atom level, on the symbol level even. So it even contains some things that aren't an atom. And then you could say, why am I looking at head 6? I mean, they're all kind of interchangeable. That's true. There's no a priori way to know where these things would come up. I mean, there's, I guess, around like 100 heads in this transformer, and they probably implement different things. So that's why this isn't fully unsupervised. You just need a little bit of well-curated data on the side. You have 100 of heads that implements different things, and then you just look at your data and find a head that happens to most closely resemble atom mapping, right? And I guess this is maybe not surprising that it's one of the later layers, because maybe the initial layers are doing some more simple stuff, and maybe the last layer is more directly pulling information that is required to sort of predict the masked thing, and then there's, I think, the second to last layer. But of course, which head it is completely random. If you retrain it, it's going to be a different one. So you basically find a head that roughly corresponds to another mapping, and you see you can find one that is, let me just finish the sentence. You find one that is matching pretty good, and then on top of that, you massage it a little bit, right? You don't want to just sparsify this, because it might not give you a full mapping. So you massage it a little bit, you have some sort of a greedy procedure to extract the mapping from this. And I think it's very surprising that it actually works, but it's a sort of an established thing published in Science Advances a few years back. There was a...
So I was just wondering about this. So wouldn't it make sense to like make it fully unsupervised by kind of like having some naive procedure, like choosing most salient head, or kind of like averaging something, or like because like you don't know which head it is, but could you like do something like this, or it would like wouldn't it work at all?
Yeah. I think maybe you could actually. I mean, okay. One thing is that you could maybe look at the most sparse heads. Maybe that would be a filter. But actually, there's also so what you can also do is it's easy to perhaps, if you have some idea of what the atom mapping is, you can sort of you can apply it in a way. You can sort of look and see how it aligns. So somehow checking an atom mapping is like an easier problem. So maybe then you don't need mapped reactions that much, because maybe you have a lot of reactions and you take, from each head, you massage its outputs into some permutations and you see how often they, how much they sort of match if you align them. So I think maybe you could get away without fully supervised data. Yeah. Anyway, that was a bit of a detour how we get these atom mappings on the atoms. But if you take a data set from somewhere, this will already be in there. So you could think of that's like a ground truth, but somebody just ran one of the tools and they just put all the atom mapping numbers in there. So once you have this, you can define these edits, right? You can define these diffs in a sort of more formal way. You can say things like, atoms 2 and 9, they used to be connected, but on the right-hand side, similarly numbered atoms are no longer connected, so something broke there. And then you can derive a reaction template, which is this like a graph rewriting rule, if you will, if you're more kind of graph-minded, which is a rule that says kind of what stuff on the left-hand side was changed and then what it's changed to, right? So you just compare the things that changed, you kind of discard the atoms that didn't, you end up with this kind of cryptic thing that basically says that there was a carbon connected to a bromium, there were 3 other atoms on the left-hand side, so there are 5 atoms that were kind of changing, and then these 5 atoms got rewired like this. And this describes what changed in this reaction, right? And you can see, for example, this matches this, right? And it says that this bromium came from here and that this came from here. So this just describes the 5 atoms that actually changed kind of directly. So you have this rule, and then you can talk about things like applying a template, right? So you could take this left-hand side here, and then you can say, I'm going to apply this, which means finding a subgraph that matches the left-hand side and kind of rewiring it to the right-hand side. And so this is where we're going for with this other class of models, which are sort of more neurosymbolic, if you will. So they will combine some sort of a neural and some sort of a symbolic component, right? And the symbolic component are these templates, right? This kind of very hard computer science rules that say what has changed. And so, and one additional thing to mention, maybe if you're missing side products, all this stuff kind of still works out. You just have some things without atom mapping numbers on them, and then you have a slightly different template. But it's still, all this kind of graph transformation stuff still kind of works out, even if you have omitted some things. And then, given this, you can design this model. And this is actually, if you looked at the deep learning reaction prediction models, this is maybe the most basic kind of model that there is. It happens to be very kind of scalable, very kind of small, and it's relatively good. So the pipeline for this is that you have some code that takes all of your training reactions that just extract these templates, so these little rewriting rules, and then you have like a big database of them, like 10,000 or 20,000 of such rules. And then for each sample in a data set, you know which rule was the correct one, like rule number 756 was the right template to apply here. And then it just turns into a gigantic classification problem, right? So then you could say that you have a molecule, and then you have some classification model that chooses one of these templates from a library of 10,000, and then chooses this one. And then you train this model with just classification, right? So it's a pretty simple model in that sense that it has just a very big classification layer at the end. So it can't make arbitrary changes. It can make only changes that have support in data. And then once you have this classification model at inference time, you would sort of predict which template you want, and then you would apply it, and the applied part is a deterministic operation now. And so these models are, this is, I would say, the most basic kind of model in the sense, most widely used. And they are nice about covering sort of a large proportion of things that could happen, because you can think of, you have this classification layer that predicts templates. So you sort them by probability and you try to apply them in this order, and that covers kind of things more systematically. And they are relatively good at staying kind of closer to the data, right? It's not arbitrary transformation and turning lead to gold. It's something that is at least has a few reactions that support it. So these kinds of models, there's one caveat which happens that, if you think of these templates, if you match them, that means finding the left-hand side somewhere in your input, in your product. You can find it in several places, so what do? You could consider all of these matches. So each of these matches can produce a different outcome, right? So you could you could consider all of them, right? As I said, you want to return a bunch of outputs, so you could consider just all of them as candidate outputs, or you can be slightly more think a little bit more and maybe make this template a bit larger, kind of artificially. So even though this template, as I said, it describes everything that has changed, you can attach some certain things in the vicinity of the changing part, and these things will be kind of copied from left to right. So they won't affect the kind of transformation that it is, but they will affect where this matches, because the left-hand side is a larger subgraph, and now it matches in less places. So you can do tricks like this, and then you have more templates, but they're sort of more specific. And then this is on the most basic models, right? There's a question. So these are the most basic kind of model for this, and now I will have a bunch of slides for maybe more interesting, more modern ones, and then we go to search.
Would it make sense to use some kind of tree search here instead of like, okay, so I guess you could apply different strategies. You can just use the argmax of the prediction, maybe you like exhaustively search the predictions, or maybe with beam search, but
you mean here?
Yeah, when you predict the next template to apply to create the next part of the molecule and then build from that.
Yeah. So, okay, so as I said, here this model, and this is part of these models that predict a single step. So they predict a single template, and that's just it. That's just the end. But what you could use, and I guess this kind of goes in the direction of what you said, maybe your templates would be just changing part of your molecule, and then maybe you would be applying several templates in sequence, and then you would like a tree search, right? And then you end up in this situation where, okay, you make these templates sort of smaller and smaller, and you have to apply more of them. And in the limit, your templates just change a single bond or a single atom, and then you have to apply like a larger amount of them. And actually, yes, so that's generally a good idea. And in the, oh my, there's going to be many slides back. There are some things that I won't talk about here, but for what you've said fits in this part. So sometimes people would define these transformations in a different way, and then you have to apply more of them. It's typically more of a beam search than a tree search, but you can certainly do this. And then it also becomes a bit of a, if you think about this, of designing this library of templates, this becomes a bit of a, if you're into program synthesis and things like this, it becomes like this problem of how do I design the right domain-specific language for my problem, right? You can go lower level or higher level, maybe lower level functions, you need to call more of them. Higher level functions, you have more different functions. So I think it's generally a kind of a good idea and sort of a deep question. And this is also things that we're thinking about.
Okay,
like
so because you care about if your compound will be chemically stable and feasible, and I was thinking that the template idea is mostly to ensure that you will build, like, for example, a ring, and not just create unstable compound or impossible compound. But you are suggesting that you would like to build a compound from bigger templates. And can you provide an intuition why you would choose a bigger or smaller template? What are the advantages?
Right. Yeah, so as you said correctly, one of the advantages of templates is that they are more grounded in the data, right? So if you go to this limit of changing little bits everywhere and changing little bonds, then you can, of course, break rings arbitrarily, and you can make things that are kind of a bit more crazy. So in the end, it's some sort of a trade-off, right? If you use this, I'm talking about, if you use big templates, right? Templates that have a big, maybe sort of big context here, and templates that just, you apply one template and that's all that describes the entire transformation. These things, the library of these things grows very fast. Even for like a small data set, you might have like 50,000 reactions in your data set and maybe extract 10,000 templates, right? That doesn't sound very good, right? You have a big few-shot learning problem on your hand because you have 10,000 classes with 50,000 samples, right? So the problem with templates is that if you have a larger and larger data set, you cover more of the chemical space, you end up with a lot of rare templates, a lot of templates that apply once. So the reason to make the templates smaller, like more minimalistic, or try to decompose them into a composition of smaller things instead of one big thing, the reason to do that is so that you have more for each kind of thing, you have more support of that thing. Whereas if you stay with this big clunky templates, then for many of them, you just have a single reaction that matches this template. So that's a trade-off that you have to think about, yeah.
Yeah, makes sense. Thank you.
And then in the end, there are many works that somehow explore this trade-off in one way or another, but I don't think it's a fully finished problem yet. So one kind of example work, without going into much detail, there is one work that is that uses this more minimalistic templates that apply in more places. And then you could say, well, what happens with this fact that they can apply, you predict a template, but it applies in many places, and you have many sort of equivalent results. So this particular paper, what they do is, if your backbone is something more like a GNN, then you have outputs that are kind of localized per every atom and per every node, per every edge, you might have an output. So one thing that people do is for example, you can predict these templates on the local level. So you can predict for each atom and each bond what should be the template if it was to be applied here, and then you can max out from all of that. So essentially, you can have a model that predicts where the template should be applied, and that kind of goes around a bit of these difficulties, right? That you don't just predict it and apply it everywhere, but you predict it in some sort of a local way. And that's one recent and maybe one kind of stronger work. And there's one more interesting model, which is from our team, which kind of builds on top of that, and has an interesting feature that it adds this component of non-parametric retrieval on top of this model. And the idea is that you train this local retro model from the previous slide kind of normally, and then you have this trained model. And then you think, how would I combine this with some sort of a nearest neighbor search with respect to the training data set? So what you can do is you can run this trained model on everything in your training data set, and then you can record all the activations across all the training data. And then you have this big store. And these are actually activations on neighborhoods, because this model is predicting, it's kind of making these local predictions. So you're gathering these local activations of the GNN. And then what you can do at test time is, well, first you have this kind of initial model that makes some predictions. But you can also see, well, my input activated this initial model in some way. Let me look up in the training data set, were there cases which were activated in a similar way? Right? You can make this nearest neighbor lookup in the space of the GNN activations. And then you have kind of two sources of truth, right? You have the nearest neighbor stuff and the neural stuff. You combine them in some way, so they actually train like an extra thing on top to combine these two sources. And without looking into a lot of the details in this figure, I guess one interesting thing about this is that you have these two sources, and this combiner, what it ends up learning is that when these nearest neighbors from the training data set, when they end up being pretty close, like the distances are small, it will give more weight to that. But when they are big, if the distances are big, it learns to give more weight to the original model. So you end up with this sort of maybe, on one end of the spectrum, you have this nearest neighbor thing, which is pretty good if you're close to your training data. But then if you're getting farther away, then maybe these nearest neighbors don't tell you much, and then you use this original model as your sort of extrapolator. And I think that's, in general, I'm skipping a lot of details here. There's a paper at the end you might have noticed on a bunch of the slides. But I think one sort of general takeaway here is that this seems to be a problem where grounding in the training data is sort of important, and then you can use this kind of nearest neighbor enhanced things. And then I have these other deep dive into search algorithms, but maybe there are questions at this point. Otherwise, we can continue. I think also I will have to probably skip some stuff at the end. So let's at least understand, how do you put this all together, right? If we have a reaction model, how do we do the actual search, right? So the interesting question to start with is, what would be the state in such a search, right? You start with your target molecule, and then you have some reaction that you sort of go back with one step. And then you have a reaction with two molecules, right? So it seems that your state should be the set of unsolved molecules, right? You can say that your state is either of these two things, because you have to solve both of them for this sort of action to give you, to bear fruit, right? So you can see it's very different from sort of normal games, right? In chess, you make a move, and then you have another board on which you play. And here you make a move, and now you have two boards, and you have to win on both of them simultaneously for this reaction to sort of count, right? So your state, at least naively, you could say your state is the set of stuff that I still need to make, and then maybe you remove the things that are purchasable, and then you kind of keep going with this. So if you go like this is called the OR tree formulation. It will become clearer later why we call it the OR tree. But there's this idea that your state is the set of things, and then each sort of colorful thingy here, this is maybe my target molecule. I'm sort of simplifying into these little drawings. And maybe you take a step, and you have a reaction that could produce this purple thing, and so now your state is this, right? And then you could do your tree search like this, so you could have some reactions, and each step you would basically take one of the things in your set of stuff to obtain, and then you would predict a reaction on that thing. Like, for example, you would take this triangle, predict something here, and then you would replace this with the precursors, right? And then you can see that one nice property of this is that now it looks more like normal tree search in a sense, right? But the downside is that your states now contain this entire sets of things, and then there's, of course, some weird ambiguities, right? You can apply things in different order, you can end up in the same place twice. One nice thing is that if you represent things like this, your synthesis route is kind of represented by a path, in the sense that you can follow a path down, and maybe these molecules are purchasable, so you're kind of done. And then this path, if you follow it down, it has some reactions, and if you kind of stitch them together, you get the tree that we had at the very beginning, in the early slides. So you have a tree of possibilities. A path down that tree gives you a synthesis route, which you can convert to a tree of its own, a tree of reactions. So that's a nice feature, that it sort of looks more like normal tree search, but it has a lot of ambiguities, and you can try to resolve them somehow. But this representation generally has a bunch of ambiguities. With the sets, you don't know which of these little things in the set to expand next, and then you can end up with these weird things where, like, you have a state that has molecules A and B, and another state has molecules C and D, and then you encounter a state A, B, C, for example. It's a new state. You haven't seen that before, but it's a subset of the union of two other states. So if you solve these other two states, you've kind of solved this one, except not really, because it's a subset. So you can see there's these interactions between these sets, and you're not really capturing that well. But if you ignore that, you can apply a lot of things out of the box to this. And then the other sort of alternative is that you think a little bit harder and you come up with something that's more specialized to your problem. So you really try hard to design a tree where there's one molecule per node, and that's it, right? And what happens with this? So you start with something, you have this reaction, and then you create this node, and it's a square now, and this will be apparent, sort of the pattern will be more apparent in a second. But there's this square that basically denotes this reaction, right? So this target molecule, right, we created one child, which is one possible reaction that could give us this target molecule, and this square denotes this reaction, right? There could be more squares with more proposed reactions. And then you would say, okay, this has two circles as nodes, and these are the molecules in that set of reactants, right? And then for each of those, you could repeat this, right? So you could predict possible reactions, and then you have these reaction nodes, and then you would again have these molecule nodes. So you end up with this funky interleaved tree, right? And you have one molecule per node, but now the price that you pay for this nice feature is that a synthesis route, if you try to extract it from this, is no longer a path, it's a subtree in this bigger tree. And the idea is that, well, this molecule, right, it had one reaction that could be used to make it, right? This reaction needs both of these reactants to succeed, right? But then this molecule has several reactions that could make it, and we need just one of them, right? So you end up with this thing where, in order to extract a particular route from this tree, you have to follow from the root. And basically, if you're in a molecule node, you just have to go to one of the children. If you're in a reaction node, you have to go to all of the children. And that's why we call it AND/OR, because it's sometimes OR and sometimes AND. So you end up with this more funky tree, and then you have to generalize your algorithms a little bit to this, right? I won't go into much detail about this, but if you think about things like MCTS, or things where you have to estimate some values of your states, then you probably have to take this structure into account, right? So maybe you say, I'm estimating some values, and if it's an OR node, maybe I care about like the max value of my children, but maybe an AND node cares about the sum of values of my children, things like this. So you have to somehow adapt to this different representation, but otherwise it's sort of non-ambiguous and it's more sort of compressed. And then to give you a bit of an idea of what kind of search algorithms out there. Yep.
So is the limitation of this AND/OR tree that like you might have the reaction that kind of splits a thing into several pieces, but how do you use that combines multiple particles into a single particle, or just kind of swaps them around in the AND/OR tree?
Right, so in these, maybe it wasn't entirely clear. So when we're doing this search, we're kind of thinking of reactions as having a single product now. As I said, this is often how they look in the data set. They have one single main product and then maybe many reactants. So then if you're going backwards, you're plugging in your current molecule as your single product that you want to make. And then you're getting a bunch of reactants, one or many. So we started with reactions in real life being many to many, but kind of in this context, we kind of think of this as many to one, having one product. And then if you're going backwards, you go from one to many. So on search algorithms, there aren't that many different variants. If you look at this, most of the popular things are really alike. So you've already seen at least one talk, I guess, yesterday that spoke about MCTS, so I won't spend too much time on this. There are other algorithms which are more like Dijkstra's algorithm or A star, if you think about this. But it's really quite similar to MCTS. Maybe it's more global and less based on these kind of rollouts from the root. But maybe one thing to note here, and this is maybe an interesting trap that is very specific to this particular problem, is that if you come back to thinking about how my reaction model is used in all of this, right? I said a reaction model that we've trained earlier is kind of like an environment. It says what's allowed. But often in search, in MCTS and things like this, you want to have some sort of a policy that tells you which moves to try first. So the simple thing that you can do, and this is what people have done, is you take the same model as your environment and the policy, basically. Like your reaction model tells you what's allowed, like the top 10 reactions that are proposed are the allowed moves in this game. But then they also have some associated probabilities, so then you use these probabilities as your policy. So you have the same model being the environment, the policy, and that works out fine until you start changing that model, and there will be a bit of a mention of that on the slide at the end. But let's for now just imagine that there's just a single reaction model here, and this reaction model defines what is allowed, but we can also use it on the side to define what has priority and what doesn't. Right, so on the MCTS side, it's mostly just pointing to papers. I won't describe what MCTS does, but one of the most influential works, I guess, early works on this, was one that used an OR tree representation. Now we understand what that means. OR tree, and it used an MCTS algorithm, kind of standard MCTS on this. And so it had some diagrams. It was published in Nature in 2018, so it kind of predates AI for Science, but it's still somewhat related because Marwin, who was doing this work, is now with us, and he's kind of my boss. So it relates still to us somehow. And this was a very kind of nice early work. You can do MCTS on AND/OR trees if you wish. You have to just generalize some of the formulas. We had a more recent paper on this. And in particular, this paper from Nature, if you want to read one paper that is sort of more end-to-end, and it gives you some nice sort of one piece of paper that tells you about a bunch of things end-to-end, this might be a good place to look into, because they had actually not only found some routes for some molecules and said, we found a lot of routes, but they, for example, did this Turing test kind of thing, where they had some reactions from the literature, some reactions from the model. They showed it to chemists kind of blind, and they asked which one you prefer. And there were some preferences, but in general, it evened out. So in general, at least under some assumptions, I guess, assumptions being the molecules you're trying to make aren't super complicated, these routes from these algorithms are sort of on par with the stuff from the literature. But of course, it's a strong assumption, and on more complicated molecules, you wouldn't maybe have these promising results. But there's a nice sort of very early work on this. And just to quickly mention, there are other algorithms which are more sort of Dijkstra algorithm-like or A-star-like, but they still work in a similar way that they have some graph of possibilities that they're expanding, and then they may be deciding what to expand. And the decision here is a bit more global than in MCTS. MCTS is based on these kind of rollouts from the root, and here you're maybe looking globally at the things you could expand and maybe choosing one of them. But maybe I would say it's not that big of a difference, right? And this particular algorithm in the original paper was quoted to outperform MCTS, although we had different experiences more recently. I have some slides later, but probably I'll skip that mostly. But these are basically the algorithms that exist, right? They are kind of all alike, similar to MCTS. But as I said, you might want to, if you look at, for example, things like AlphaGo, right? You have some policy, and then you're improving the policy. And I said in a second that your policy, you're using your environment as kind of doubling as a policy. But then, if you want to be really kind of ambitious, maybe you want to update the policy. And you can do that. I mean, in the end, it's similar to what you do in kind of other MCTS in games and things like this. When you gather some experiences, you compute some maybe values for your states, and then you update that. It's just that there's this one trap, and we think some of the works fall into that trap more than others. But the trap is that if your model of the environment and your model of the policy are kind of the same model, and you start updating that, it's kind of like changing your game to be easier to play. And it's not a very good thing to do in general, right? You don't want to, if your reaction model is specifying what reactions are allowed, and then you're like, wait, but I'm not getting many routes from this search, so let me just change my model so that I get more routes. Maybe you change your model to get more routes by making the model sort of unrealistic and by making it more permissive. So, you have to be careful about this. We have at least one kind of recent ICML paper where we make it super explicit when we just split these two models, and you have two models that start out as the same, one of them being environment, one of them being policy, and then once you update, you only update one of them, and the other one you keep constant, and then you kind of avoid this pitfall. But it's just something to keep in mind. I have this last section, but I'll probably just very quickly skip through them, because maybe there will be more questions at the end. But this is maybe more sort of interesting to somebody that has maybe some prior experience to compare with our experiences. Are there any questions at this point, or should we just keep going? This one, I guess, yeah.
Hello. Okay. Regarding the Monte Carlo tree search here, what would be the metric here? Because in RL we have like a Q function, and what exactly are we computing here?
Yeah, so what would be, for example, a metric for success in a way? So what you could measure is, for example, you could measure like solvability in a sense. So you could measure if I had a given state, in what proportion of rollouts. I mean, the equivalent to games, right? In games you say what proportion I won, and here, in what proportion of rollouts I went down to a state that was fully solved, right? So you could measure some sort of a solvability.
Okay, but it's the solvability. Is it related to if this compound is like true compound, like a chemical stable compound, or the solvability means something different?
Solvability would mean that, so you're assuming that you're only following the moves proposed by your reaction model. That's kind of fixed, and then you are done if you're in this OR node, say OR tree, say formulation. You're done if your entire set is just purchasable compounds, right? So then that's a success state. So then, at least if you're doing this states are sets kind of formalism, then it kind of maps to games pretty well. So you can say your state is solved if it's just all purchasable compounds, and that counts as a success. And then maybe if it's mostly purchasable compounds, that's like a partial success if you wish.
Okay,
yeah.
Thanks.
So that would be the thing that you're at least kind of propagating up the tree would be this kind of solvability. Or you could say things like, I guess, the number of routes that are in that tree, but that opens another can of worms, right? Because it's quite hard to, given this graph of possibilities, extract how many different routes are there, and it might not be a very meaningful number to extract anyway, because maybe many of these routes are kind of very similar and they differ on some detail. there's one more question.
In the local template classifier model that you showed, do I understand correctly that each node is classified separately into the available templates?
Yes, each node and each bond is classified. So each node kind of predicts if I was one of the nodes that would be changing, what would be the template that would be affecting me? And then some of the nodes might be predicting, oh, I wouldn't be affected by any template. And then you have many of these predictions for each node. You have some predictions of templates, and then you have to somehow prioritize them. So you sort them maybe by probability and try to apply them in this order.
Yeah, this prioritization part was interesting to me. What happens if, because in the templates we have multiple nodes interacting in the same, let's say, process. So what happens if different nodes predict different templates?
Yeah. So what you would do is, say you would take one node, right? It would predict some template that affects maybe many nodes. And then you would try to apply that template generally in that molecule. You would apply it generally because you have software that can just apply a template kind of generally anywhere. And then you would see, did it actually get applied on the node that predicted it? If not, then something is off. We really want to have this template be applied at the node that led to its prediction, right? If you have a template that left-hand side has several nodes, then basically this template has more shots at being predicted, because each one of these nodes could theoretically predict this template, and if it's with high enough probability, it would be considered to be applied. But I don't think this work does this thing where maybe there are atoms A and B, and they really disagree, like one of them predicts this template, the other one doesn't. If one of them predicts the template highly, it will already be tried. But I think it would be it's probably not explored sufficiently yet, but I think it would be a good idea to somehow make it a bit more structured and maybe have more nodes voting on what they want to be part of and things like this.
Thanks.
So that's a very good idea, I think, yeah.
So these methods looked like they were mostly operating on how to go from reactants, how to go from products to reactants, but you did not mention the reaction conditions anywhere, so the catalyst, temperature, and so on.
Yeah.
So have you thought of incorporating that into this workflow?
Yeah, that's a good catch, right? I sort of glossed over that. So kind of ideally, yes. Ideally, you would have a model that takes into account the conditions, and depending on the direction, it's either an input or an output, right? In the forward direction, that would be part of your input. In the backward direction, that would be part of your output. So it would be outputting, to get to this product, you could use these reactants with these conditions, right? So ideally, you would consider conditions. In practice, often you don't consider them, partially because they might be missing from your data set, and also in the backwards model, they would be part of your output. And maybe the conditions could be quite varying, right? It could be a temperature, so that's a number. It could be a molecule as a catalyst, or it could be some like instructions of what to do. So there are some works that deal with them, but they're generally kind of hard to deal with. So people sometimes or usually just omit them. But it's also not that bad. I mean, at least it depends in what setting you're asking the question of retrosynthesis. So one setting we're more interested in the drug discovery setting, where you're kind of trying to figure out. Is this me making the sound? Or I don't know. In the drug discovery setting, you're just trying to figure out if this molecule could at all be synthesized, and then you make some synthesis plan, and then maybe it's not a very, you're allowing yourself to spend some time on it, and the chemist maybe fills in these details that are missing. But then maybe there's another setting when you already decided on a molecule that you want to make, and then you want to make it as efficiently as possible. And then maybe there the trade-offs are slightly different. And then you would also care about more different details, right? If you're in the second stage of like, I want to make a lot of this stuff cheaply. But we're more in the stage of like, can we make this stuff at all to check if it makes sense? And yeah, so I guess one shortened answer would be that we don't deal with the conditions much, but the chemist basically has to do this to fill in the blanks in a way. There's one more question, yeah.
Okay, that's loud. You said that the environment model and the policy model are the same one, the same model. So, and is it necessary?
Yeah, I think that's a good point. So I think it's often the same model, sort of out of laziness in some sense, right? You could say, the environment model tells you what's allowed, and the policy should tell you what would be a good move to apply to get to sort of smaller chunks, right? So in theory, they could be completely different. In practice, the reaction model, it was trained to kind of predict real reactions, but the real reactions were the things that chemists have tried, which they did for a purpose of building bigger things from smaller things. So there is a bit of a bias in this environment that maybe makes it a reasonable policy. That's what I'm saying. So it's not very decoupled, but ideally you would decouple them. So ideally, probably what it makes sense to do is you have this environment model that defines what's allowed, and then maybe that's like an initialization of your policy model. So certainly you don't, if you keep them fully the same model always, that's kind of just out of simplicity and because it tends to be like a good starting point, but yeah.
Okay, thanks.
Any more questions? Do we have like 10 minutes more, right? So that's now the section that I will mostly skip. And maybe it's more of a section that's interesting to people that have worked in this area more, because there are some hot takes and things like this. So basically, we had a lot of kind of generally what this is about. We spent a lot of time making maybe new things in this field, but also a lot of time trying to understand existing things and reproducing results and running open source models and stuff like this. And one thing that we found that was kind of weird is that we found that a lot of the published models, when we tried to run them, the numbers ended up different, and in both ways, really. Like you could get much worse numbers, or sometimes like get much better numbers like this. And then we tracked down many of these things to some reason. Some of them were pretty trivial. One maybe interesting thing is that one of the published models, you could get much better results by just removing the duplicates from your predicted reactions. And then on one hand, you can say, well, cool, that's like a trick to get better numbers. But maybe a deeper lesson here is that it's not a trick in the sense that you do it or you don't do it, and it's just either way the same. You should do the kind of post-processing that you expect to happen in real life, right? So if your search won't have duplicate actions, because why would it, then you should also remove duplicate actions when you're evaluating a single-step model. That's what I'm saying. So there were caveats like this. There were other cases when the models ended up being worse because reasons. Because they basically, the setup was slightly different. And then you basically end up with apples to oranges comparisons, and then people copy numbers, and then now the numbers have spread everywhere, and we can't correct them. So there were things like this. There actually, I will mention this at the end. There's a paper that contains all of this stuff. We had other experiences with comparing search algorithms. We had a workshop paper on this, and we, for example, found that the newer A-star kind of like algorithm, really MCTS, you can get it on par with this algorithm if you get the details right. So for example, there are some important details like caching, which is basically to say that if you're running this search, sometimes you call the model on the same input, and the question is, do you call it again, or do you have a cache of the outcomes? And then details like this can have a big impact. So we had things like this. We had a lot of different thoughts. I will not go into them in detail, but in general, like an overarching theme is that this is maybe a non-standard, retrosynthesis is a non-standard ML problem, and there are many traps involved, and there are many metrics that are kind of a reasonable proxy for something, but they aren't the actual ground truth thing, and if you focus too much on the proxy, then you end up with weird results. So we had just a bunch of different thoughts and good practices, and this leads me to this thing, right? So we're building, and by building, I actually mean that we have some secret code, and we're releasing parts of it chunk by chunk. So we have this recent repository that we put on GitHub. It's not popular yet in any way. We haven't advertised it in any way, but it has already a bunch of useful things with retrosynthesis and reaction models. You can do various nice things. So actually, if you want to have some sort of a hands-on experience, you can take this repo. There's some notebooks there, so you can have a notebook. You can like put a molecule. It will find you some routes. It actually will visualize them for you and choose like a diverse subset and whatnot. So it's maybe a nice thing to start out with, and we are planning to add more stuff to it. Weird sounds. So then That's maybe one pointer for you. The other pointer is that all of this, I said, we've reevaluated a lot of things, some confusing takeaways. We have some kind of spicy takes and sort of best practices and pitfalls. So we have a sort of work in progress paper that we haven't put out yet on arXiv, but if you email me, I can always just give you a draft, because we're just still sort of changing it. That's why we didn't put it out there fully. So that's one. And I have this final slide. So, just coming back to the team, so I'm from the AF science team. It has many nice buildings. I'm from the Cambridge one, but importantly, this is sort of a global initiative with many offices, and most of the projects, all of them are split across places or across continents. So it's supposed to be a relatively ambitious thing that is trying to make some real impact on these projects, not only publish papers, not only salami-sized things, but really do something more maybe substantial. So you have a big list of people that somehow contributed to some of these things. Some of them, like the earliest things, the people aren't even in MSR anymore. So people that kind of touched the things that I've shown here. I have some links. So this is, if you want more about AI for science, this is like a page with what projects we have, for example. There's a lot of things across like chemistry and physics. Drug design is just one part of it. There are people working with PDEs and sort of weather prediction. We have some cool professors. We have Max Welling, Frank Noe, and people like that. So you can read more here. There's a link that gives you these slides if you want stuff in the slides, for example, pointers and things like this. And these are the two repos that I mentioned. So the generative model and the sort of work in progress retrosynthesis stuff. And I think we have maybe a few last minutes for last questions, and that's all from me. Yeah.
So thank you very much, Krzysztof, for the cool talk. So yeah, we only have like 3 minutes for questions, but then probably you can talk also to Krzysztof during the break.
So at some point, yeah.
Thanks for the talk. If I understand correctly, backward synthesis looks like we take a molecule graph and then we just have to change the edges in a sense, and then we get a different looking graph. Mm-hmm. So could the problem be formulated in this way that we take an input graph that is the product, and then we just predict the probability distribution over the edges?
Yep.
And that's going to be our output graph.
Yeah, that could be one formulation. So for each edge, and also for each non-existent edge, I guess, because you have to also form edges. So maybe for each pair of nodes, really you're predicting the diff. You could do this, but then you end up in this problem of sort of modeling correlations, right? You can't just sample from all of these probabilities independently, because then maybe they won't form a coherent whole, right? And especially given that there are many possible answers, right? Most likely these probabilities won't kind of match up. So we'd have to do some sort of an autoregressive process where maybe you decide one of them, and then you maybe recompute the probabilities conditioned on the first choice. And this is the Megan model from some of the folks on Molecule 1. It does basically this. And it's one model. It has some good properties, but it also has some downsides. It's basically you have to deal with this tricky sort of autoregressive process of choosing something and then updating your beliefs based on this and choosing another probabilities. So there are tricky parts to it, but there's certainly one way to approach things, yeah.
Okay, thanks.
So maybe let me ask the final question before we move on. So I was just wondering about the architectures. Like, I'm curious about your like insider view, like about transformers versus like GNNs. Like, do you gain a lot by using GNNs generally in these problems?
Right. So I guess one thing in this Hall of Fame between GNNs and transformers, one thing to include, which isn't as sexy, is sometimes you even use very simple models which use, I think Morgan fingerprints appears at some point. This is like a featureization method in chemistry that turns a molecule into like a bit vector. And then even an MLP on that big vector is often a competitive thing. So that's one thing to note. But if we don't use that, we would use some sort of standard message passing based GNNs. You could use graph transformers as well. I think we haven't yet gotten sort of an improvement switching from GNNs to graph transformers, but I'm hoping we can. Some of the models I've shown here, like the local retro stuff, it does have like this graph transformer flavor. They have like a GNN and then like an all-to-all attention on top, so it's kind of a mix. But yeah, so I think all of these models are kind of applicable, but you know, I would say often the differences in performance aren't that big. So even a jump from like a MLP on fingerprints to like a GNN is often like a very minor jump for, I guess, various reasons. I mean, the datasets aren't that big. I mean, even the proprietary dataset that we've had to pay for is like a 3-4 million reactions, and maybe the more public ones are more like 500,000. So maybe the datasets aren't sort of big enough. Maybe you need a foundation model to train it on many tasks, and of course we're looking at that as well. So yeah, I guess that was a bit of a longer answer. So yeah, the differences between the architectures, at least for these tasks, aren't that big, but certainly GNNs sometimes give you an improvement, and transformers as well are useful. Yeah.
Okay, so thank you so much. So Krzysztof again.